Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on the side, and we are looking at some things out of Chapter 4 in the Big Ideas Math 2 textbook, where we are solving quadratic equations not just by factoring, but by a bunch of other methods. And in this particular video, it's solving by graphing. Now, I don't know when you're watching this in this series of things. I might be even recording something out of order, but this is section 4.2, solving quadratic equations by graphing. And so it comes off the heels of chapter 3, where we solved quadratic equations. Assume a lot of things come in standard form, I think, to begin with, but I might be able to factor them and show x-intercepts and things like that. So you do have to know how to graph, because I'm going to go a lot faster on that. I'm going to say, here's just how you graph it. I mean, here is the graph, and here's what I'm doing with it. If you don't know how to graph it, you're going to have to go back into some of those things. When I hit negative b over 2a, when I hit something that's factorable and get my x-intercepts, which way it faces up and down, stretch factors, all that jazz, because solving by graphing is finding where they intersect with some lines, even if they are lines written in slope-intercept form. So, just keeping that in mind, let's go straight into the lecture portion of this thing and see what they're going to talk about and what we're going to do, where we're going to have a pretty hefty problem set, I do believe. We're going to solve quadratic equations by graphing, use graphs to find and approximate the zeros of functions. That must mean I'm going to need a calculator, so I didn't know that was coming up. And solve real-life problems using graphs of quadratic functions. Previous phrases, x-intercept and root and zero of a function, they all kind of honestly, they all mean the same thing. They're all the same. When they ask for one, they really mean one versus the other, ultimately, which is just nice to know. And I might have mentioned that in the past. Solving quadratic equations by graphing. A quadratic equation is a nonlinear equation that can be written in the standard form ax squared plus bx plus c equals 0, where a doesn't equal 0. In Chapter 2, we solve by factoring. You can also solve quadratic equations by graphing. And there are going to be a lot of other methods that we choose, but seeing the visual graph and seeing that's going to be fantastic. So, what value of x gets us 0 is the question that is often asked in this section. So, to solve by graphing, we are going to write it in standard form, this thing, or it's set equal to 0, and we're going to graph the y equals version of it and find the x-intercepts. Here's what we're really doing. We have an equation, we have an expression right here, and we have an expression right here. 0 is indeed an expression. I want to know what value of x, what x gives me 0. Okay. What we're doing, take a look, once again, they say graph the related function y equals ax squared plus bx plus c. I want to make the graph of the left expression, and I'm technically also going to make a graph of the right expression. See where they said find the x-intercepts? X-intercepts are values of x when y equals 0. We're not only graphing this, but we're also technically, I don't know if we're graphing y equals 0, but we're comparing it to the x-axis. I want to know what value of x gets me the same y as this y right here. And remember that, because we're going to be using that in future problems when it's not set equal to 0. So we're finding x-intercepts. So we solve x squared plus 2x equals 3 by graphing. What we're going to do is subtract the 3 over, set it equal to 0, and draw this graph. I'm not going to explain why the graph is drawn the way it is right now, but boom, here is the graph, right? Y equals x squared plus 2x minus 3. Use your whatever you're going to do. Now, well, I guess I don't want to graph by factoring, because factoring will give me the intercepts. But when we graph and we find out where it crosses the x-axis, those x-intercepts are the answer. If I plug negative 3 in for x into this equation, I'm going to get 0 for y. If I plug 1 into x in this equation, I'm going to get 0 for y. And that shouldn't be new. We've done that stuff before through graphing. I think that just using this method with quadratics while graphing for ourselves is all interconnected now to say wherever they're crossing are the solution sets. So here's that double check here. Now what they do is they don't double check with the new equation where it was set equal to 0. They double check in the original equation to see if they get 3 on the left and 3 on the right. Note that this is going to be very important for the future to say if it doesn't equal 0, what we're going to do. Alright, so let's look at another one. Now this one only has one real solution this time. Last time we had 2 solutions because it crossed the x-axis twice. This time when we solve this by graphing, we're going to add 16 over to the side. We're going to graph this guy here the way that we do, and the graph happens to look like this. Now this only crosses the x-axis once at x equals 4. It's the only solution. How can a quadratic, something that comes back up, only hit the x-axis once? If the vertex is on the x-axis. And we've seen that before as well. Not very often, but we have seen it before as well. Only one solution. This is where you have what's known as a repeated root. They say you can also solve the equation by factoring. Now, we're going to solve by graphing. They're just saying that here's another way to get that same answer. You factor here, it's a perfect square trinomial, x minus 4 times x minus 4, so x equals 4, a repeated root from both of these instances right here. The only answer. It's possible to have no real solutions as well. It's possible to have no real solutions as well. And this is another method that we're going to see ultimately down here. So let's take a look at both methods. First method is getting everything on one side of the equation. They decide to add x squared over to get everything positive. X squared plus 2x plus 4 equals 0. We graph it as we do. I'm going to use the negative b over 2a concept for a lot of these, just to get the vertex that way. Hopefully you know what that means. And take a look at this graph. When it comes to solving by graphing, guys, we're trying to find out when this thing crosses the x-axis. When do I get 0 for y? And the answer is I never do. Notice that there are no x-intercepts. That means it has what's called no real solutions. And that's the phrasing we're going to use, that literal one. Don't just say no solutions. No real solutions is that set. That's the first method. We've been using that method already, at least in these notes, setting it equal to 0 and then graphing y equals that. The alternative is graphing it as they are on separate sides of the equation right now. Look at this, negative x squared. We're going to graph y equals negative x squared. Look at this 2x plus 4. We're going to graph y equals 2x plus 4. This is a linear equation. This is a slope-intercept form, y equals mx plus b. So kind of a prerequisite. Not going to get deep into here's how you do it. I'm going to graph it as I do, but I'm not going to get explanation as to why. I'm not teaching slope-intercept form. Excuse me. But what we are doing here, why are we doing them as two separate y equals this, y equals that? Technically, we were already doing that. Before we were graphing y equals x squared plus 2x plus 4. And whether or not you say you're graphing y equals 0 is the horizontal line that makes the x-axis. So when does this cross the x-axis? Like that. Now, why are we doing this? Besides, we have been doing it because, and hold on, my phone's been chirping. I'm going to probably get that in 1 second. Because we're trying to find what value of x gets me the same output. What value can I plug in for x here to match what value I plug in for x there? Ultimately, in this case, the answer is nothing. If you look at these two graphs right next to each other, here's y equals 2x plus 4. Here's y equals negative x squared. These graphs never intersect. They never intersect. Wherever they would intersect, however, is we're going to seek the x value of that. I don't care what the y value is. I just care that when I plug in the x value, I get the same y value. Give me 1 second. My phone's just telling me a lot of things. Let me just go ahead and clear this thing out as I say that out loud. Vibrate. Okay, so normally I do that beforehand. I forgot. So if they do intersect, we'll note what they are, and guess what? They would intersect at the same x values for this graph if we had that. So I'm sure we're going to find values where we do it. So concept summary, a number of solutions of quadratic equation. Guys, you can have two real solutions if it crosses the x-axis twice, or if they intersect at two different spots. There are two solutions. You could also have one solution if that thing, the vertex, hits the x-axis once, or if they cross tangentially once, which we'll possibly see. Meaning if a curve intersects with a line just at one point only like that, it can only have one solution there. Or 0 solutions if it never has any x-intercepts, when we set it equal to 0 in that kind of way, or if they never intersect. These are 3 sets of ways you can have solutions to quadratic equations: 2, 1, or 0. More often than not, you have 2, because that's just the nature of how they solve and stuff. But if they create problems where there's 1 and 0, then they have that as well. Okay, finding the zeros of a function. Hey, zeros are the same thing are x-intercepts. Recall that a 0 is an x-intercept. So when they find a 0, the basic difference here is this time they have a y equals set up for the equation. So what do? You graph and find out where they cross the x-axis. For what values of x does y equal 0? It's not a different question. It's asked differently. You're doing the same thing. We're graphing this and finding where we hit the x-axis. What values of x give me 0 for y? And here's a double check. When you graph this one, it crosses at -1 and 3. When you plug in -1 to the equation, you get 0 out. When you plug 3 into the equation, you get 0 out. The zeros are the x-intercepts, -1 and 3. No difference. Approximating the zeros, this is where I said a calculator, in fact, let me get mine popped up right now. This is where I said a calculator is likely going to be needing to be used. If they say approximate, they're saying let the calculator tell you some of the information. And I don't yet know how this is going to show and what we're going to do, so I popped it up just in case I have to use it later. Here's y equals x squared plus 4x plus 1. And we're going to approximate the zeros to the nearest tenth. You can notice that they don't cross exactly at any integer values. So what we do instead is we make, they say make tables. I'm going to use this with my calculator, but make tables and start to use increments of 0.1, meaning instead of going from -4 to -3 to -2 to -1, we go from -4 to -3.9, -3.8, -3.7, etc. And we find which x gets us the closest y of 0. In this case here, you change in signs. These are our y values from x's. They're positive, and suddenly they turn negative. Between this positive and negative, somewhere they hit 0, somewhere between -3.8 and -3.7. And then also between -0.3 and -0.2, it also goes from negative to positive again. That means somewhere in between they hit 0. So if they say round to the nearest tenth, find the one that's closer to 0. -0.11 is closer to 0 than 0.24. Therefore, x would be -3.7 when rounded. And -0.11, once again, closer to 0.24. And x is closer to -0.3 when rounded. So -3.7 and -0.3 are the approximate solutions to that. And I'm going to use, like I said, a graphing calculator. The one where I can make tables out of and show those when they pop up. You could approximate 1, 0 using a table and then find it. Yeah, okay. I won't talk about that right now. Okay, real life problem. A football player kicks a football 2 feet above the ground. Okay, well, I'll say this. I have been doing some word problems in the past. I linked another, I just did a review video that talked about some word problems, and I linked to an old word problem video, one that I think is kind of popular on YouTube by search. If you type quadratic word problems, I think it shows up. So there are more of these that will be talked about here. I'll talk about what they show right now. But if you want to get a bigger in-depth model on what kinds of word problems you can see, especially involving gravity, you might want to look at those a little bit more. This video should cover them, but that one might be a more in-depth. It's an hour-long video for 6 questions. So you might want to look at that more than just what I'm going to do here. I feel like I want to rush myself more here. A football player kicks a football 2 feet above the ground with an initial vertical velocity of 75 feet per second. This function represents the height in feet of the football after t seconds. So if you notice, the 2 feet above the ground, this 2, the constant, is not only your y-intercept, but it's also the initial height of the graph. So the y-intercept in standard form is the initial height, because at time 0 is when the football's kicked. So at time 0, you have a height of 2. That's what explains the 2 feet above the ground. 75 feet per second, this is initial velocity. I believe we've seen that before in previous questions. And -16 has something to do with gravity, so that way the ball can come back downward. So there's a parabolic arc. You're going to see a lot of those when it comes to those. Find the height of the football each second after it is kicked. So here they substitute 1, 2, 3, 4, and 5 into here and get some values out for h. You notice when it goes negative, the model no longer applies because a height of a football can only stay above ground. A height of 0 is when the football hits the ground. So somewhere between 4 and 5 seconds, the ball does hit the ground. Maybe they'll have us approximate that. But we plug in these numbers until we run out of possible range values. We should stay above 0, really. Part B, use the results to estimate when the height of the football is 50 feet. So again, they're asking you to do an estimation. So we say, hey, it's somewhere between 0 and 1 second because it's somewhere between 2 and 61. It's likely closer to 1 second because of the 61 here. They might have us use a table. Let's see. The height of the football is 61 feet after 1 second. 8, from part A, you can estimate the height of the football at 50. So based on the function, it's reasonable to estimate the height of the football slightly less than 1 second and slightly less than 4 seconds. So they're not really rounding. They're just saying that 61 is closer to 50 than 2 is. Now, this isn't linear, by the way. It goes like this, and it works its way back down. But 50 is closer to 61 than it is to 2 by a considerable margin. So it's closer to 1 second than it is to 0 seconds. So about 1 second in, and somewhere between 3 and 4, probably closer to 4 than it is to 3. 46 is a lot closer to 50 than 83 is, so around 1 second in and 4 seconds in. They say between here, but slightly less than 1 second, slightly less than 4 seconds. To determine, part C, using a graph after how many seconds is the football 50 feet above the ground? Didn't we just do that? Using a graph after how many seconds is the football 50 feet above the ground? So that's kind of the same question. Are we doing, using a graph? So this time we draw the graph for it. And then what we're going to do is set our equation here equal to 50. The line y equals 50, and I don't see them drawing it, but the line y, because they set it equal to 0. The line y equals 50 would have been a constant line here, and we could see where it intersects. But we're going to set it equal to 0 by subtracting over and approximating those values using the table as we did before. So I'll make sure to do those problems again, but you can actually find the zeros using the zero feature. I'm going to go ahead and do that, and we can get the exact times at 0.76 seconds and 3.9-ish seconds right here when it actually hits the 50. So we approximate it first, we get the exact later. Okay, that's it for the notes portion. Let's go ahead into the vocabulary and core concept check. 4 questions. Number 1, what is a quadratic equation? I don't know how to answer that. A quadratic equation is an equation with x squared as the leading term. An equation with x squared as the leading term. You could also say ax squared plus bx plus, plus, what did I just do? Plus bx plus c equals 0, where a does not equal 0. So a needs to, if a was 0, then it wouldn't be a quadratic equation anymore, right? So a does not equal 0. B and c can be 0, right? I can have y equals x squared. That's quadratic. So that totally works out for me. All right, which one doesn't belong? Which doesn't belong with the other 3? Explain your reasoning. Couldn't tell you off the top of my head. I can tell you some things about it. They are all quadratic equations. I can write them all in standard form. One of these is set equal to 0, whereas the other 3 are not. I imagine that's where they're going with this thing here. So if this is A, this would be B. So one is not like the others in that one is already set equal to 0. Now, there are potentially other things about them of which I am not certain, such as there could be some that have 2 x-intercepts and some that have 1 or 0 or what have you. I don't really see that in this setup here as a certainty. I believe all of these at least hit the x-axis. I think all of them hit it twice. I'm just going to say that. I believe all of them hit it twice. So there's that. There could also be a thing where some have rational solutions and some do not. And I think all of these are irrational solution sets as well. I don't see any of these as factorable. So I believe B is the different one to set equal to 0. It's in standard form already, basically. In standard form. Number 3, how can you use a graph to find the number of solutions of a quadratic equation? It's all depending on, now if we have it set equal to 0, right, just like that B, if we have it set equal to 0, it's all about how many times this crosses the x-axis. If a quadratic equation set in standard form is in standard form set equal to 0, you count the number of x-intercepts that the graph has. So the number of x-intercepts matches the number of solutions, which matches the number of solutions. Let's see if I can move that thing over here. So if you have 2 x-intercepts, there are 2 solutions. If you have 1 x-intercept, there's 1 solution. If you have 0 x-intercepts, there are 0 real solutions. So that would be number 3. Number 4, how are solutions, roots, x-intercepts, and zeros related? They are the same thing. All those words, whoopsie. Sometimes, I'm not going to say the word factors matches, but it relates to them. If they said factors, then it's the factored form gives you the intercepts. They are the same. They are all about finding out the value of x when y equals 0, or finding out the values of x that give you the same y value out. But they are the same. That's how they're all related. So a lot of synonymous terms there that we're getting ready to use. If you see any of them, and they say, here's a section where you find x-intercepts. Now here's a section where you find roots. Now here's a thing where you find zeros. They're all asking for the same thing, which is pretty cool. All right, numbers 5 through, I think, 65. We're going to go to town on those ones. Let's take a look at what we have. I got PDF stuff down below for graph paper, for the problem set, all that. I think I'm going to use the tall graph paper when we do these. If y'all don't mind, let's go ahead and get started. Get your calculators ready just in case we got to use those in the future. Keep in mind, I'm not going to teach you how to graph again. I'll be doing the graphs, but that should have been based off previous problems. All right, use the graph to solve the equation. These are all written in standard form set equal to 0. Let's start with number 5, 4, negative x squared plus 2x plus 3 equals 0. Once again, we are going to graph y equals. We're going to graph, and this is the only time I'm probably going to write this, but we're going to graph y equals negative x squared plus 2x plus 3, and we're going to see where this crosses the x axis. Oh, they give you graphs right there. I'm sorry. Okay, so they give us graphs. So perfect. Use the graph to solve the equation, not graph and solve it. So if you look at this graph right here, you can see right here they cross at this guy and this guy. This is, remember, y equals 0. Y equals 0 is this line right here. That's really big. Is this line right here. So we are trying to see when the blue crosses the red. Where does it cross the x-axis? They cross at -1 and +3. So I'm not going to graph it. No way. But I'll graph them later. So the solutions, the values that give you 0 out are -1 and +3. I should probably use the word or +3. But those are the two different values that give you that. Okay, I don't have to do any graphing here. Number 6, and I'm not double checking right now, but if you substitute -1 into here or 3 into here, you will get 0 out. Number 6, x squared minus 6x plus 8 equals 0. Here's that graph, and like I said, I'll be doing graphs later. Looks like they're crossing at x equals 2 and x equals 4. Those are the values of x that'll get you 0. I'll just put a comma. Equals 2 and 4. So just finding the x-intercepts. Number 7, x squared plus 8x plus 16 equals 0. Look at this graph here. It only crosses the x-axis once, and that's just at -4. It bounces right off of that and doesn't hit again. Only one solution, x equals -4, only. It's a repeated root. Number 8, you see that this thing does not cross the x-axis at all. There is no value of x I can substitute into here to get 0 out. No matter what, it'll always be less. Remember, the y values that you get, like if I plug in -2, I'm going to get -2 for y. If I plug in -4, I'm going to get this value for y. So whatever x value I get are the y values we get out. We'll never get 0. We'll always stay negative. There is no real solutions to this thing. There are no real solutions, only what are called imaginary solutions or complex solutions. All right, numbers 9 through 12, we're going to write the equation in standard form, and that's all they ask you to do. So this is a nice, I'm not going to say a slow build because we're doing them quickly, but this is a nice build into the kinds of problems that we'll be doing after. So for standard form, we have to subtract the 12 over, which means we set that equal to 0, and that's all they're asking you to do on it. Later, what we're going to do is be able to graph this straight up and try and find where it crosses the x-axis, but that's all we're doing on it, number 9. Number 10, you have -x squared equals 15. Now, there's more than one way that you can set something in standard form. You can either subtract the 15 over, or you can add the x squared over. If there's ever an excuse that you can make to make your x squareds positive, you do it. I'm going to add x squared to both sides, and I'll get x squared plus 15 equals 0. It's better to have put it that way than to have more negatives, especially if you could make your leading term positive. And that's what I did there. Number 11, I think it's kind of the same thing right here. And again, there's more than one answer, so let me put the other one. This is fine by subtracting 15 over from both sides, but I'm really going to prefer this one, so I'll say preferred here. Number 11, we have 2x minus x squared equals 1. For the same reason here as before, as far as what's preferred, I'd rather add x squared over and subtract 2x over. So we have this. And standard form is in descending order of degree, so I'm going to go with this. Even if I subtracted 1 over, y'all, which is fine, I'll have x squared as negative, but even if I do, my x squared term does have to go first. So it would be -x squared plus 2x minus 1 equals 0. And then number 12, 5 plus x equals 3x squared. Once again, I'll keep my x squared term positive by subtracting the other two things over. So 5 plus x equals 3x squared. Let's subtract over x. And when I say subtract it over, notice how I write them on the left side. Subtract it over and subtract 5 over, set it equal to 0. I imagine we'll be graphing these afterwards, solving by graphing to do that. Yep, solve the equations by graphing. See examples 1, 2, and 3. And listen, there were two methods that we chose here. We're going to be using the method where we set it equal to 0 and find where they cross the x-axis. So let's go off of that. X squared minus 5x equals 0. Now, I wonder if, I was mentioning I might want to solve by factoring and all that kind of stuff, but, excuse me, not solve by factoring, but graph by putting it in intercept form, factored form. I wonder if I want to do that, because then that means that I get the answers from it. See, they don't tell you how to graph. It's just kind of cheap if I do it that way, though. I want my graph to confirm that I get those intercepts, so maybe we got to use standard form as it is. That means let's find the vertex by using negative b over 2a for the axis of symmetry, negative b over 2a, which is 5 over 2, which is 2.5. So there is an axis of symmetry at x equals 2.5. We start right off the bat with one of these guys. Right. Yeah, close enough. Let me try and fix that. At x equals 2.5. We got to find the y value off that, guys. So we're going to substitute. Now remember, this is we're graphing y equals this, right? So we're looking at for y equals x squared minus 5x. We're going to be looking at plug in 2.5. 2.5 squared minus 5 times 2.5, which is 6.25 minus 12.5, which is negative 6.25. So the vertex is at 2.5 comma negative 6.25. This is an interesting one because, well, okay, there's something else I know about this where standard form would have helped. I'll say this is an interesting one because even if I use my stretch factor going 1, 1, 2, 4, etc., I was going to say I don't know what actual points I hit, but I'll show you what we do hit. We have a y-intercept of 0. So 3, 9, 6, 7, 8, 9. And then, I don't know, 4, 16, if we want to put that. That's going to be upright, I think, here. So I can fit a lot of these points to graph. Now, I'm going to draw this curve through, but what's interesting is that although I didn't solve by factoring and getting my x-intercepts out, because the point is I want the graph to show you the x-intercepts, if I graph this out of standard form reveals something else as well, which is your y-intercept. Standard form reveals that this would have been a plus 0. My y-intercept would have been 0, which is also my x-intercept. So that's a point that this actually hits, you can tell. And when we reflect across, 2.5 away is this other guy right here. So it does hit both of these points at x equals 0 and x equals 5. Never mind the fact that my graph seemed to have hit those. I can use that as a corresponding point for the y-intercepts. So x equals 0 and 5 through the graph. Okay. Now, I could have factored this thing out and I would have gotten y equals x times x minus 5, in which case it's going to reveal that, yes, indeed, x equals 0 and x equals 5. This is a tough section to talk about because it's one of those things where we already know how to solve by factoring. So it's like, how can I stop myself from using that as a method? Or, you know, I think at that point we can kind of just confirm that things work the way that they're intended to when we see that. Okay, number 14, we have x squared minus 4x plus 4 equals 0. Now, I already know what this graph will be looking like here. We're only going to have one solution. But let's go ahead and graph y equals x squared minus 4x plus 4. So let's find the vertex. The x value is at negative b over 2a, which is 4 over 2, which is 2. Now let's find the y value by substituting 2 into here. 2 squared minus 4 times 2 plus 4, and that becomes 0. So your vertex is at 2 comma 0, which is also an x-intercept, right? 2 comma 0. So the vertex is on the x-axis. Now, I technically don't need the rest of the graph. I found it, but they said solve by graphing, which means give us a graph. So this was going to hit 1, 1, 2, 4, 3, 9, and 4, 16. When I say that, I mean how far away that they go from the vertex. And there's the graph, and it's only hitting the x-axis once at x equals 2. X equals 2 is the one and only solution to this equation. If you did factor this, you would see that this factors into x minus 2 quantity squared as well. But so yeah, x equals 2 is the only solution to this thing here. I plug 2 into here, I get 0 out. It's the only number that works. Number 15. X squared minus 2x plus 5 equals 0. Off the bat, I can tell you it's not factorable. Not factorable does not mean there's no solution, but I can imagine there's potentially no solution here. We'll see. All right, so x squared minus 2x plus 5 equals 0. Let's find that vertex. The x value is at negative b over 2a. Opposite of 2 over 2, which is 1. The y value, substitute 1. 1 squared minus 2 times 1 plus 5, that's 4. So our vertex is at 1, 4. And notice that this graph goes upward. It's a positive 1. So this graph goes upward from 1, 4. 4 is already above the x-axis. So if we're at 1, 4, notice the y-intercept is 5. And by the way, I didn't mention that for the other one. Notice how this y-intercept was 4, and we hit 4 right here, even though my graph was kind of poor on the drawing. This y-intercept is 5, and that makes sense because going over 1 up 1 from here will get us those points. And doing the rest of this graph, look how this graph goes upward from already being above the x-axis, which means we are not going to hit the x-axis. If we don't hit the x-axis, that means there are no x-intercepts. And if there are no x-intercepts, that means there are no solutions, no zeros, no roots, no values of x when y equals 0. There are no real solutions. Now this is one I could not have graphed by factoring because it wasn't factorable. And that doesn't, once again, not factorable does not mean no solutions. We actually saw an example in the example set where we had to approximate our solutions. It wasn't factorable, but they're rational. However, since we're not using the calculator in this set, it's hard to imagine that we are going to have ones that are not factorable but do have solutions. So, in order to solve these, they better be crossing very good x-axis values. Let's start once again with that vertex. This one does look factorable, by the way. I think we're going to get two solutions. This x is at negative b over 2a, which looks to be 3. Let's substitute 3 into there. We're going in the y equals equation. We get 3 squared minus 6 times 3 minus 7. That's 9 minus 18 is negative 9. Minus 7 is negative 16. So our vertex is at 3, negative 16. And with my tall graph, I can go ahead and do that. Plot that point. We're going to get a bunch of points on this one, guys. And see where they cross the x-axis. So 3, negative 16 is all the way down here. These stretch factors are all 1. I think they're making it nice and easy. I don't know. Yeah, 1 or negative 1 it seems to be. Unless we set it equal to 0 on the other side. So let's see where this thing's going to hit right here. By the way, y-intercept of negative 7 over 3 up 9 seems to agree with that fact that that would be negative 7. And over 4 up 16. And look, we hit right there and right there. For good measure, I'm going to go 5 over and 25 up, which looks like that. And that's probably all I can fit, which is quite a few points. So this curve is going to hit there. That's one of my x-intercepts at negative 1. And it's going to come back on the other side at what? 7? So x equals negative 1 or x equals 7 are my two solutions to this one, solved by graphing. Again, I'm doing it out of standard form. X equals negative 1 and 7. That does mean that this would have factored into x minus 7 times x plus 1, right? And you would have gotten 7 and negative 1 from that. But they do ask you to graph, not factor. Number 17. X squared equals 6x minus 9. This is one that's not set equal to 0, but let's go ahead and set it equal to 0 so that we could graph this equation in full, x squared minus 6x plus 9, in that standard form. We graph y equals this now, and then we find where it hits the x-axis. What are those x-intercepts? That's our basic goal. So the vertex x value is negative b over 2a, which is 3 again. The y value will be, looks like it's 0. So 9 minus 18 is negative 9, plus 9 is 0. So your vertex is at 3, 0. Once again, vertex on the x-axis means it's the only x-intercept that's going to exist, and we're going to be able to build the rest of the graph from here. I'm going to be graphing y equals this guy. This is the one that we're going to be graphing here. So we are going to get 3, 0 as our vertex, and a 1, 1, 2, 4 kind of relationship here. And if you notice that when based off this graph, 3, 9, we're going to hit y-intercept of 9 right there and reflect across. And 4, 16. And you can see it only hits one time at the vertex at x equals 3. At x equals 3. So only one answer, which means that this was a perfect square trinomial when written in this form. X equals 3 is it. All right, and then number 18. Negative x squared equals 8x plus 20. Once again, there's more than one way to do this when it comes to how you want to write out standard form. Either you subtract over the 8x and the 20, and then you graph that, or you add the x squared over and you graph that. Now listen, so I'm going to add the x squared over. But now listen, you would get two different graphs as a result from it, but they would still get the same solutions. They'd still be the same x values, or lack thereof. They'd still be the same x values that get you your answers in the end. So this vertex from here is going to be x equals the x value, negative b over 2a, which is negative 4. When we substitute negative 4 into that equation in standard form, we'll get negative 4 quantity squared plus 8 times negative 4 plus 20. 16 minus 32 is negative 16 plus 20 is 4. So your vertex is at negative 4 comma 4. This is what I'm going to be graphing. That's a positive 1x squared. That means this thing will go upward. This graph is, the vertex is already above the x-axis, which indicates that this will not cross the x-axis at all. So we're going to have a no real solution case that's going to look like this. 1, 1, 2, 4, 3, 9, here. And we never cross the x-axis, so no real solution in this case as well. No real solutions. Just the imaginary ones. The y-intercept would have been 20. I can't fit that here. I get close. Here's 17. But I never actually quite hit that one. So no y-intercept, but no visible y-intercept, no real solutions. Okay. All right, we're going to move on to the next set. Let me take a hit. Oh, no, we still got 6 more of these to do. Okay, well, let's keep whiz-banging through it then. Number 19, we have x squared equals negative 1 minus 2x. Let's add these over, but in standard form, the 2x will go first. I know where this one is going. Vertex x value is negative b over 2a, which is negative 1. The y value is 1. So it's going to be negative 1 squared. Plus 2 times negative 1 plus 1. 1 minus 2 is negative 1 plus 1 is 0. So your vertex is at negative 1, 0. Once again, on the x-axis, vertex is there. There's only going to be one solution, and that will be negative 1. But to graph the rest of this, remember we're graphing this one. That's a positive 1 stretch factor. So 1, 1. And that makes sense. 1 was the y-intercept. 2, 4. 3, 9. 4, 16. And there's your beautiful parabola. See, I'm going to say it once again. The book doesn't ask you how to graph this thing. And I'm not saying, hey, you should do intercept form, factor this thing and do whatever. I'm not sure what they're actually encouraging you to do. But if they do it the way that they did it as of old and they say use a table, it's going to take a while to do. Hopefully, if you've been watching some of my videos, you've been able to catch on to how I'm using this. All these stretch factors are 1. That makes that part really easy, the 1, 1, 2, 4 kind of thing. But even if you doubled it or halved it or flipped it over, whenever we do, hopefully you're feeling pretty comfortable whenever I use those. Okay. Number 20. X squared equals negative x minus 3. Let's go ahead and add these things over. We will get x squared plus x plus 3 equals 0. And let's find the vertex. Looks like it'll be a fraction for the x value. X is negative b over 2a. b is 1, a is 1. That's negative 1/2, which is also negative 0.5. I'll write it like that. The y value will be, I don't know which one I like. I like fractions more myself, but I've been living on word problems so long, I was thinking maybe we should write it that way. I'm going to use the fraction version. I hope that's cool. So negative 1/2 quantity squared plus negative 1/2 plus 3. That's 1/4 minus 1/2 plus 3, which is negative 1/4 plus 3, which is 3 is 12/4. So 11/4. Now 11/4 is 3.75. Excuse me, 2.75. So yeah, so your vertex is at negative 1/2 comma 11/4, and that's where you're probably looking more on the like I want the decimals, Mr. Robinson. Well, it depends on what's being asked of you. But negative 1/2 is here, and 11/4, or 2.75, is right there. Kind of funky looking graph, but more importantly, this graph goes up. Positive 1x squared, I go over 1, I go up 1, like so. Looks like we're not going to hit this x-axis. Over 2 up 4. So everything I'm doing now is purely academic. I mean, no pun intended. This is just an academic exercise of, we already know this graph's not going to hit the x-axis, but we're just graphing the parabola as indicated. So it's going to go, let's get a better curve. It's going to go like this. Now check this out. This does confirm that we hit the y-intercept we intended to. The y-intercept based on this equation is 3. On this equation here is 3, and this does seem to hit at 0, 3, but it never hits the x-axis, and that's what we're looking for. There is no real solutions to this thing. That is number 20. Number 21. 4x minus 12 equals negative x squared. Let's add x squared over. Let's make that one positive. Again, whenever we have the ability to kind of make that so. Already not in standard form. Let's do it. This looks factorable, and it looks like we'll get 2 solutions out, which is nice, but let's find it through our graphing means. So x is negative b over 2a. The x value of the vertex. X is symmetry. That looks like it'll be negative 2. The y value is going to be negative 2 quantity squared plus 4 times negative 2 minus 12. 4 minus 8 is negative 4, minus 12 is negative 16. So your vertex is at negative 2, negative 16. There aren't too many ways with these. So I'm surprised they're only doing stretch factor of 1. I guess they don't want to overdo it with you guys and going back and saying, hey, remember how to do this when the stretch factor is not 1. But you're going to have some of the similar, if this needs to cross the x-axis at integers, you're going to hit some of the same y values for the vertex. You'll hit a y value of negative 1, negative 4, negative 9, and negative 16 if the stretch factor is purely just 1, because that's what leads you to getting values that look like they're going to hit right here and right here. So those values are hit. Hopefully you know what I'm doing by counting these up. That's 5 over and 25 up. As when I hit the x-axis, I went 4 over and 16 up, because 16 is 4 squared. And it looks like we're going to hit those x values. What are they? Looks like we hit x equals negative 6 and x equals 2. So negative 6 and 2 are the 2 x-intercepts for this graph. That's what we get. Those are our solutions, negative 6 and 2. And that's how this would have factored. X plus, this one, x plus 6 times x minus 2. So negative 6 and 2 are them. Number 22. Also looks factorable. 5x minus 6 equals x squared. Subtract 5x over, add 6 over. Of course, we get x squared minus 5x plus 6 equals 0. For the vertex, your x value is at negative b over 2a. 5 halves. I'll keep with the fractions. I'm going to be mean. That's 2.5. 2.5. The y value for this is 5 halves squared minus 5 times 5 halves plus 6, which is 25 fourths minus 25 halves plus 6, which is negative 25 fourths plus 6. 6 is 24 fourths, which is negative 1 fourth. So your vertex is at 5 halves, comma, negative 1 fourth, like so. So 2.5, comma, negative 0.25, like that. When we go over 1, we'll go up 1. Over 2, up 4. So it does hit somewhere. Over 3, up 9. I think like. And over 4, up 16. Kind of weirdish points to hit, but they do count. Okay, this graph will be black. My apologies. Now, where's it hitting the x-axis if you were to kind of be perfect-esque with this? Well, look at that. 2 and 3. Now, is there a way that you know that for sure just by the graph alone? No, I can't know for sure and know that my graph was perfect with it. Because what if it was 1.99? You know, we don't know, no. I can say those do work. I can say this is factorable. This would have factored into x minus 2 times x minus 3. So there are ways to confirm it. By the way, the y-intercept there is 6, 0, 6. But that's the factorization of that guy. So yeah, this thing does hit at x equals 2 and x equals 3. Once again, I don't really know how they're going about. I don't know how they're going about graphing it for you. If they're, say, use a table, plug these things in. But listen, if I plug 2 in for x, I'm going to get 0 for y. I plug 3 in for x, I'm going to get 0 for y. They did say solve by graphing. My graph seems to hit those 2 points right there. All right, number 23. X squared minus 2 equals negative x. Let's add x over. This thing's also factorable, so I should get 2 solutions from this guy. So the x value, and it's going to be the same kind of look, negative b over 2a, which is negative 1/2. So this isn't going to be much different from the last one that you had as far as it's in between and what's it really hitting. The y equals negative 1/2 squared plus negative 1/2 minus 2. That'll be 1/4 minus 1/2 minus 2, which is negative 1/4 minus 2. 2 is 8/4, so negative 9/4. Negative 9/4 is negative 2.25. So your vertex is at negative 1/2 comma negative 2.25. It's not going to be, whoops, negative 9/4, I'm going to say. It's not exactly like the other one, but it will be somewhere in between some things here. So once again, we're going to kind of have to rely on our graph to say what integers do we hit. And if you see the factorization of this equation, you should probably also be able to know what they will be. So let's check it out. So negative 1/2 for x, negative 2.25 for y, there-ish. And stretch factor of positive 1. So 1, 1, 2, 4, 3, 9, and 4, I think 16's right here. Okay. With this curve, I shall formally declare the x-intercepts to be negative 2 and 1. So see where it's kind of hitting on these things. X equals negative 2 and x equals 1. If we factor this equation, we will see x plus 2 times x minus 1. We can also confirm the graph works the way it's supposed to. Y-intercept of negative 2 also seems to align. But negative 2 and 1. We can try and plug those in, see if we get 0 out. You will. You will. X equals negative 2 and 1. Again, hopefully solving my graphing is working as intended. And then number 24, we have 16 plus x squared equals negative 8x. Now, I haven't used the second method yet. I assume they're going to force us to use the second method on future problems. I'm not sure, but we'll get to it when the path crosses. Because I don't know if this was part of the other examples. X squared term's got to go first. Let's add 8x over to this guy, and plus 16 is 0. Looks like a perfect square trinomial. Looks like there's only one solution. The vertex x value is negative b over 2a, which is negative 4, the only x value. The y value will be negative 4 squared, 16, plus 8 times negative 4, minus 32 is negative 16, plus 16 is 0. So your vertex is at negative 4, 0 on the x-axis. This graph will be going upward in the 1, 1, 2, 4, 3, 9, 4, 16 scenario. And you're going to see that that's the only x-intercept that we have right there, where the rest of the points hit here. And we should confirm to get a y-intercept of 16. And confirmed, y-intercept of 16. X-intercept, only x-intercept of negative 4. That is our answer. X equals negative 4. Let's just finish off this graph and then write that in, and we'll be good. X equals negative 4. Okay, and that is 24. 25 and 26, error analysis. Describe and correct the error in solving x squared plus 3x equals 18 by graphing. It looks like they only graphed y equals x squared plus 3x. They never use the 18 in any way. And you have two different options and methods. The method one we've been looking at was we had to subtract 18 over to begin with in the scenario. Okay, so they only graphed this portion. They never included the 18. Now, what's interesting about this problem is, I'm trying to think, never mind. I think this will have solutions. I was going to say what's interesting is that we won't hit the x-axis at integers, but we will actually. So we can correct it ourselves. My problem is my graphing window doesn't go all the way down to negative 18, which is what we're going to do. So they ignored the 18 outright. 18 either needed to be, y equals 18 needed to be its own equation to find where the original graph intersects of y equals x squared plus 3x intersects. Or, and the way I'm going to do it, or they should have subtracted 18 over and graphed y equals, let's do this, y equals x squared plus 3x plus minus 18. And found the x-intercepts. Okay, so that's what we're going to do. We're going to go ahead and see x squared plus 3x equals 18. Subtract that over. X squared plus 3x minus 18 equals 0. And let's go ahead and graph that guy. Now, this is factorable. It factors to x plus 6 times x minus 3. So we should get x-intercepts of 3 and negative 6. They got negative 3 and 0. Obviously incorrect. So for the vertex, the x value. And notice they also didn't tell us how they graphed this one either. So they're probably using the negative b over 2a concept. Negative b over 2a, which is negative 3 halves. That's also negative 1.5. The y value, let's substitute negative 3 halves in for x. And we're going to get 9/4 minus 9 halves minus 18. That's negative 9/4 minus 18. 18 is 72/4. So we're going to get negative 81/4, which is negative 20.25. It's even lower than my graph shows. So I don't know how I'm going to do this really well with you guys. I could have, I don't know, I could have done differently here. But negative 20, so, vertex is at negative 3 halves, comma, negative 81/4. Negative 3 halves is negative 1.5. I'm going to draw this axis of symmetry this time. Negative 1.5 here. And then negative 20.25 is a little down the list. So I'm going to have to do the best I can when I say like 1, 1 and things like that to just give you the best version of approximations that I can. I can't see. There we go. So here's negative 17, negative 18, negative 19, negative 20, negative 20.25. Sure, all the way down there. 1, 1 is at negative 19.25. 2, 4 is at negative, I guess, 16.25. So am I a little too far down there? Because this would be here. Maybe it's a little too far down in the first ones. I can go maybe a little less. Kind of like that. Sure. Notice, again, y equals negative 18 is the y-intercept. It's the y-intercept. So it would hit like probably like right there. 3 over 9 up from 22.5 is negative 11. Wait. So 16.25, negative 11.25. Is that really? Oh, I'm sorry. Maybe that is the right height, because 16, this is negative 15.25. There we go. That makes more sense. Okay. Negative 11.25 would then be right here. Hard yelling outside. 4 over up 16. So negative 4.25. This is a little beyond. We were just correcting their error. 5 over and 25 up. Let's at least get that last one. 25 up from that is 4.75. Yeah. 4.75, like so. Okay. Let's see how this graph will pan out for us here. So we're going down like that. That is a curve, believe it or not. That's not straight. And down right here as well. Whoops. Kind of missed my spot. That's okay. It's sharpening a little more over time, just slightly, ever so slightly. Now I hit x-intercepts right here. This is what we're looking for at x equals -6 and x equals 3. Now, like I said, this was factorable to x plus 6 times x minus 3. So we would have gotten those two answers there, and it looks like that's where they are. A little tough, especially when my graph goes out the scale and they're already decimals. They don't really help us, but they do say correct it, and we did. All right, number 26, describe and correct the error in this one by graphing as well. Now, you can see the scales on the graph go by 3s. That's not my favorite, but it looks like the graph is all good. But they said the solution is x equals 9. Okay, it's not x equals 9. I don't know how to... Oh, it looks like they got the y-intercept. I was going to say, I don't know how they got that number. They probably looked at the 9 and they were good to go. The graph is correct. The graph is correct. However, they noted the y-intercept instead of the x-intercept. The x-intercept is -3. Therefore, x equals -3 is the solution. That's all I'm going to do. Everything else is correct on the problem. Their answer is wrong. The graph is correct. That works. Number 27. So we're already starting the word problem set. All right, sounds good. Number 27, modeling with mathematics. The height y in yards of a flop shot in golf can be modeled by y equals -x squared plus 5x, where x is the horizontal distance in yards. Interpret the x-intercepts of the graph of the equation. Okay, they only mention interpret the x-intercepts. I'm not going to use -b over 2a if I don't have to. I'm going to factor a -x out and I get x minus 5. That gives me an x-intercept of 0 and 0 and 5. So this graph in a very, I'm not going to call it a rough sketch, but kind of rough-esque, because I'm not finding the vertex for you, unless they ask me to later. They don't. But this thing, it goes, you know, there and there. And here's the thing. Now, I don't know what the vertex exactly is. I don't really care about that. They're not asking. They said interpret the x-intercepts of the graph of the equation. I don't know if they mean in the context of the situation, but take a look at what I'm also showing, guys. I'm not showing this graph go downward like this with arrows. This is a golf shot that's shot right here, and it lands right there. I don't know about the graph part exactly in between, but I know that this is where it hits. It's a negative graph, goes upside down. It goes from the origin to there. So interpret the x-intercepts. X equals 0. This is A. X equals 0 is where the golf ball is struck on the ground. And x equals 5 is where the ball lands 5 yards away. Okay. That's the interpretation in my book. That's what I'm seeing. Part B, they say, how far away does the golf ball land? Well, we just answered that. The golf ball lands 5 yards away. That's kind of all I can say. The golf ball lands 5 yards away. The golf ball. So we just interpreted, interpreting the x-intercept stuff is also the answer to part B. Unless I'm misreading something, that's exactly what we're trying to do for that thing. Oh, maybe what they're trying to say is not really what the x-intercept values are, but the fact that they hit 0. The x-intercepts are the value where the ball is struck and lands. So they don't actually want to say what the numbers are yet. So how about that? The x-intercepts are where the ball is struck and where it hits the ground again. So how about that? And then the golf ball lands 5 yards away because that's where it hits the ground again. I like that. All right, number 28. The height h in feet of an underhand volleyball serve can be modeled by h equals -16t squared plus 30t plus 4, where t is the time in seconds. Okay, now what I'm noticing here, and I don't know how much I mentioned this in the lecture portion, I stated that there are going to be some problems down the line. that I did some word problems with this kind of stuff. But you know what? This is only about intercepts. This isn't about the vertex and initial height and stuff like that. So if you want to get a lot more on just quadratic word problems, talking about the maximum height and stuff like that, I don't think this is going to do those. This is more about intercepts. Anyway, we have h equals negative 16t squared plus 30t plus 4. You're gonna get a lot of questions involving, I was gonna say balls, just involving sports things, because gravity's gonna take effect, and we know that things can go up in the air and come back down. They do a lot of things with that, so just get used to a lot of sports related things. Or jumping, or whatever. The height h of an underhanded volleyball serve can be modeled by here. Okay, do both t-intercepts of the graph of the function have meaning in the situation? Explain. Okay, this is a good thing to talk about here. Again, we're not going to draw the actual perfect graph, but... And I'm trying to decide how I want to come up with this. If you guys are aware of anything on this, because I don't know if we're doing the full graph or not, we can either factor this thing if it's solvable by factoring, I don't really know, or just come up with the understanding of the graph. For the y-intercept is the initial height of this thing. This is the underhand serve, 4 feet off the ground, and then it hits some max height and then comes back down. So it hits the ground here. But notice there's another one over here that is to the left of the y-intercept, or the h-intercept, I should say, where time is negative. This t-intercept does not apply here. So as far as t-intercepts go, no, only one of them matters. The other one is time before the ball was struck. It's not even technically a part of the model. No, not both t. The left t-intercept is negative. Therefore, it is time before the ball is struck and does not apply to the model. Therefore, it does not have meaning in this situation. So that is part A. Now, I didn't graph. They didn't actually ask us to. Eventually, they might ask us to. Part B, no one receives the serve after how many seconds does the volleyball hit the ground? Okay, so that's this guy over here. So listen, I'm not going to do a graph the same way by standard form and vertex and stuff. My negative b over 2a will be ridiculously weird, and I don't think I can fit the full graph in the way that I'd like to with all the stuff. But what I can do is, I guess, factor it. Either they didn't ask us to approximate it, so I assume this is factorable. So let's look at part B. Let's factor out a, let's write it again. Definitely going to factor out a negative, and it looks like a negative 2. So I'm going to factor negative 2 out, and we get t squared, 8t squared, minus 15t minus 2. So this factors into some 8t times 1t plus minus 2 and plus 1 like that. So this guy, this is where t equals negative 1/8. This is the one that does not apply. An eighth of a second before the volleyball is struck does not apply. But t equals 2 does. Time is 2 seconds. 2 seconds after the underhand volleyball serve is, served, it's going to hit the ground. I didn't graph it. I gave you a really rough graph here. Here's where t is negative 1/8. And here's where t is 2. And just kind of solve by factoring using that idea of where it would hit the ground again. Remember, this was 4. H equals 4. 4 feet above the ground is where the volleyball was struck. Didn't get the max height. They didn't ask for it. All right, numbers 29 to 36. We are going to solve the equation by method. Okay, here's that method 2 thing. Using method 2 from example 3. So method 2 is all about not setting it equal to 0, but instead graphing each side as if they were their own little graphs. So 10 minus 3x. So we're going to graph two different equations here. They're y equals this and y equals that. I'm going to call them instead f of x and g of x here. So we're going to graph f of x equals x squared. We're going to graph g of x equals, I'm going to rewrite this as negative 3x plus 10. I still want some form of standard form. Where do these intersect? What x values? Those are the same things. So notice, if I added 3x and subtracted 10 over and found x-intercepts, those x values are going to be the same x values I find here where these two graphs intersect. There'll be different y values than the x-axis, likely. There'll be different y values, but they are the same x values where they intersect. That's all I want to find. For what y do I get this? For what x's do I get the same y out on this side and this side, and that's the whole goal. Now, these graphs should be significantly easier for us to do as far as they probably don't require a lot of standard form stuff. I can use a lot more factoring biz the way I want to here because my goal is in x-intercepts. My goal is where these intersect. Y equals x squared is the simple at the origin. You go 1, 1, 2, 4, 3, 9, 4, 16 upward. So like this. So these will be more basic graphs. I don't have to use negative b over 2a likely to get any of these things. I might have to shift horizontally or vertically a little bit. Maybe I do have to use negative b over 2a here and there, but the point is, how does this intersect with the other guy and where? So you definitely want to plot as many points as you can fit. It's not x equals 0 is the answer. Negative 3x plus 10, y equals mx plus b. Here's my b of 10. My y is down 3 over 1. Down 3 over 1. You can see where it hits this point right here. Down 3 over 1 like so. And that's one of my solutions. Now, the tricky part about this is I don't know if I have enough room to be able to hit this other side. Up 3 left 1, up 3 left 1. So this one unfortunately runs out of window range. I can imagine it's going to hit at negative 5, 25. I couldn't tell you right now. That's an unfortunate thing that they take me out of my window range. Now, I don't know if I have the means of really wanting to change that for you guys right here. Let's imagine if this graph kept going in that direction, that this blue would hit up here at negative 5, 25. Now, why do I know that? Because if I did set this equal to 0, which I didn't have the luxury of really talking about, but if I added 3x and subtracted 10, and you can see here this would factor to x plus 5 times x minus 2. Now, where did these intersect? These intersected at x equals 2. Where did these intersect? Apparently somewhere at x equals negative 5. You can see that I would have gotten negative 5 out and 2 out. So x equals negative 5 and 2. I cheated. I cheated by saying what I assumed it would hit coming out of window range and showing the factoring version of it. But that's what I'm looking for, guys. What value of x? Listen, the y value is 4. I don't care about what the y value is. I care that when I plug in 2 for x here, I'm going to get the same value for y, which happens to be 4. Doesn't matter what it is, it just happens it's the same. Just like here when I plug in negative 5 for x, I'm going to get 25 for y on both of those. I don't care what it is, I just care that they are the same. They are not x-intercepts anymore. They are not set equal to 0. That is now our goal. Number 30. 2x minus 3 equals x squared. Hopefully this one pans out a lot better than the last one. 2x minus 3 equals x squared. Let's call this guy f of x and this guy g of x. We're going to graph y equals this and y equals that. That's the basic crux of these problems. Which, like I said, will probably go faster. So 2x minus 3. Negative 3 is the y-intercept. Let's rise 2 and run 1 over and over again. Like so, and fall 2, run 1 to the left. Maybe it won't go faster. There's a lot of points I got to plot. Okay, now let's compare it to y equals x squared, which looks like this. 1, 1. Oh no, look at this. They'll never hit. 2, 4, 3, 9. Don't force it. If it doesn't hit, it doesn't hit. Now, that's just another way of saying that this graph also wouldn't have had any x-intercepts. If so, will this hit? I don't think so. Oops. And it goes like that. So never actually touches. If they never touch, they have no real solution. That means if I put these things on the other side of the equation, x squared minus 2x plus 3, I never would have had any x-intercepts, no matter how close they look. No real solutions. So we can't solve that one. Number 31. 5x minus 7 equals x squared. Okay. Also not factorable, so let's see what they're going to talk about with solutions for this one, if there are any. F of x over here, so y equals this, and g of x over here, y equals that. 5x minus 7. So negative 7 is the y-intercept. Up 5 over 1. 1, 2, 3, 4, 5, 1. Okay, like that. 1, 2, 3, 4, 5. Okay, I think this is in a straight line right here. Looks good. All right, y equals x squared, once again. It's just this guy. It's going to look extremely closer. This is a tougher call, I'll tell you what. This one, if I didn't know that this wasn't factorable, this would be way too tough to determine what the heck this thing's doing. This is a cruel... These are cruel questions, guys. Notice this thing is going to be coming away from it just a little bit, and I do have to be precise in this drawing to really emphasize what's happening here. So this goes right here. Oh, man. This goes right here and hits right here. Oh, man. Look at this. I can't go off of that part of the graph. Oh, man. Oh, man. Oh, man. Oh, man. This is a cruel question, y'all. Do those graphs ever hit? I don't think so. You might say, Mr. Robinson, you got to move this a little bit to the left. All right. I don't think those are hitting still. Wow. Now, keep this in mind. If I subtracted 5x over and added 7 over, also not factorable. Again, not factorable doesn't mean there aren't any solutions, but I don't think they're going to let us have any. If this was a 6, it's factorable, and it would hit in 2 places. In this case... No, there are no solutions on this one. In this case, there are no solutions. It's really close. That's really cruel for them to do, especially when we had one that goes off the graph and then, you know, we have to scale differently if we really wanted to, which I didn't. But here you'd really have to change your scale if you wanted to show that spread. Like I could have changed x's every 2 increments or something like that, but oh, it's really close. Look, they probably let you use graphing tools with your calculator to check it all out. I was going just off that. Number 32 should pan out. This should be fine. 32. Let's look at some that actually hit. X squared equals 6x minus 5. So we're going to graph y equals x squared. We're going to graph y equals... If they're all y equals x squared... Oh, they're not after this. I was going to say, if they're all y equals x squared, why don't I just have a copy and paste of that? But not this time. So... y equals x squared is here. This one should hit twice. I just hope it's within our window range, because, you know, otherwise it's a little bit difficult to talk about what they are. Because I'm already pretty tall on my graphs, right? Going up and down 17 units is pretty bold, man. All right, so there's y equals x squared. Here's y equals 6x minus 5. I start at negative 5. I'm going to rise 6 and run 1. It's going to hit at that same point here. Rise 6 and run 1 again is here. Rise 6, run 1. Okay, this one does look like it goes off the graph as far as... It should hit twice, but I don't know if I'm going to see the other time that it does hit. It's going to be a little farther away that we're going to actually be able to see it. So that's too bad. I won't be able to actually see the other one, as long as I was counting over up 6 correctly here. So this one, guys, is going to do a little bit like that. You can see that blue doesn't hit green right here. These are right on top of each other right now. The green is right on top of blue. It's once we hit x equals 5 once again. At x equals 5, we are going to hit. And that's just my knowledge of this graph here. X squared minus 6x plus 5 equals 0. This factors to x minus 5 times x minus 1. Now we saw x equals 1 right here. X equals 1. X equals 5 is later up there. So once again, a little bit off my graph. I apologize. There's really nothing I can do about that with my scale. You said change the scale. I didn't anticipate this, and it's just something I can't control right now. I'm not intending to. But yeah, that's where those would intersect here. I just hope they can fit more within. Listen, change the stretch factor, guys. I'm fine. I'm fine with you making it more compressed or something. Totally cool. Let's get some that we can actually see hit. Number 33. X squared plus 12x equals negative 20. Now this time, in terms of graphing this guy, keep in mind, I'm going to write it like this. Oh, this is mean in its own right. I'm going to do this kind of through its factoring methods, right? I can have x times x plus 12, which means the x-intercepts, these are not the solutions, these are just the x-intercepts. The x-intercepts are 0 and negative 12. Now what the problem is here is that negative 12 is off my graph set. So if I were to graph this guy, and this isn't the whole graph, right? This doesn't give me my vertex and stuff. Boy, guys, I'm gonna have to change some scales here. I'm gonna have to change some scales. Let's keep going. The axis of symmetry before I graph it. Axis of symmetry is x equals negative 6, halfway in between 0 and negative 12. Let's substitute negative 6 into here to get the y value. That's negative 6 times 6, which is negative 36. So my vertex is at negative negative 6 comma negative 36. Okay, you've convinced me. I'm going to change my scales on this one. I'll go by 2s, and even that's troublesome because it'll just fit off the graph. Y equals negative 20, I would have had to fit off the graph as well. Now that was f of x. G of x, y equals negative 20, is just a straight line, but at negative 20. So let's do this. Let's go by 2s. 10, 20, 30. Negative 10, negative 20, negative 30. And let's go by 2s here as well. Negative 10 and 10. Okay, so let's do green first because I already have the color and stuff. Y equals negative 20 just looks like that. Literally, it's just a straight line. It's just a shifted down version of a graph. X squared plus 12x crosses at 0 and negative 12. Now that they go by 2s, I can fit that. Negative 36 is even still, what's at negative 6 here, comma negative 36. It's still 1 off the graph like that. So here we go. 1, 1. Oh, these go by 2s as well. Let's just go by 2s. 2, 4. 4. Is that right? 2. 4, 16. So 4, 6, 10, 12, 14, 16. I'm always really bad. Is that right? 4. No, 16 is up here. 4, 6, 8, 10, 12, 14, 16. Okay, that's where it crosses. So 16 here. And then apparently we hit 6 comma 36, which is fair, and that's what works. 8 comma 64 would have been up. What's 64 from 30? 28. So we would have hit right here and right here. So going by 2s does work. It's just pretty big. So we're going to hit like there. Sorry about the kind of wonky look. This is a little stretched for my tastes. But what x values are we hitting here and here? Remember, these are going by 2s. So it's negative 2 and negative 10. So x equals negative 2 and negative 10, which, if you added 20 over, it would be x plus 10 times x plus 2. So negative 2 and negative 10 do seem to work. All right, over an hour in. Number 34. We've been over an hour in for 17 minutes, so it's not a surprise. I just didn't know. X squared plus 8x equals 9. Please be a little better for me. So this is, once again, f of x on this side. Let's factor an x out as a GCF. And we will get x-intercepts of 0 and negative 8. The vertex, x value is negative 4. So f of negative 4 is negative 4 times 4, which is negative 16. Okay, this will fit on the graph here at negative 4, negative 16. Negative 4, negative 16 right here. Stretch factor of 1. I can not fit 636. Okay. So there's my f of x graph. The g of x graph, the other one is going to be y equals 9. And okay, I think I just hit 9 up here. So we just got to find what x values those are. So cool. One that's actually going to fit. This actually works now. So y equals 9. That's this line right here. That's our g of x equation. They're just flat. It's not slope intercept. Well, it's slope intercept form, but your slope is 0. So g of x equals 9. Okay, where are they crossing? Where are they intersecting with each other? Here, x equals 1 and x equals negative 9. X equals 1 and negative 9. Those are your values. Okay, number 35. negative x squared minus 5 equals negative 2x. Okay, as far as f of x and g of x goes, two different y equals equations. Let's graph both of these. I don't really need to say more on these other than just graph them. This one, it's a negative x squared graph, so it goes downward, but this thing also translates 5 units downward. Negative 5 is not only the y-intercept, but it's also the vertex. We're 5 units down, and this goes over 1, down 1, over 2, down 4, over 3, down 9, etc. So it's going this way. Y equals negative 2x is it has a y-intercept of 0, and will go down 2 over 1 to the right. To plot some of these points, I don't think these will intersect. This goes down 2 over 1 like so. No, it won't. So it looks like that. I'm not going to go all the way up to the top. You guys hopefully understand what that looks like. I can just go through here and tell you what it would look like going through the top like that. But the point is, these guys do not intersect. So it looks like that. No real solutions. Okay. Number 36, same kind of thing. Hopefully these ones do intersect. Oh, I know how these will intersect. I was waiting for one of these. Do you know what's going to happen? 36. Negative x squared minus 4 equals negative 4x. I got an f of x here. I got a g of x here. Let's take a look at those two graphs. Y equals, y equals. Negative x squared minus 4. It's just like negative x squared minus 5. It's the same thing. It's just shifted 1 up from where it was. So it's at negative 4 instead. So 1, 1, 2, 4, 3, 9. Like so. Okay. So there's that portion. Okay, the other side, negative 4x. Again, y-intercept of 0. We're going to go down 4 over 1. Down 4 over 1. And we hit that point. Now, these are really hard to tell what's going on unless you really got a good concept of this graph. Let's get this on the other side. But it definitely hits together at one point. We just saw what it was. So let's draw that line and see what's going on. Like that. Here's the thing. I said that it hits there, and it does. That's the only place that it hits together. It doesn't touch multiple times over and over and cross back. It just touches together right here only. And I hope that that graph is a good indicator of that. The x value of this is what we're looking at. That's x equals 2. X equals 2 is the solution to this guy. You can imagine that if you move x's over and stuff like that, you'll have a perfect square trinomial that factors to one real root. This would be the equivalent of having the vertex on the x-axis if this was written set equal to 0. And that's the one and only answer. All right, find the zeros of f on numbers 37 to 42, and we're given the graphs of those. So finding the zeros, guys, we're just looking at the graph and finding where they cross the x-axis. I'm not scoffing at the problem. I'm just saying that don't let it overcomplicate what they're asking you to do. I'm going to go based off what they show us. I'll write out the equation for you, but it looks like it's crossing at x equals 0 and x equals 2. So as far as that goes, f of x equals x squared minus 2x. I'm not going to copy down the graph again. They have it for you. So x equals 0 and 2. We can double check that. 2 squared is 4, minus 2 times 2 is 4. 4 minus 4 is 0. 0 squared minus 2 times 0 is 0. And those are the two answers. So with the graph, finding the zeros means find where they cross the x-axis. So number 38, f of x equals, we got x squared plus 3x minus 4. Look where they're crossing the x-axis here. Looks like at negative 4 and 1. So x equals negative 4 and 1. I don't know. Okay, here's what I'll do. They show it on the graph. I'll at least factor. Listen, I'll at least factor these for you guys. That's kind of, it's a weird question for them to just, you know. I'm trying to drag this thing over. This isn't working. Okay, anyway. Let me kind of do this again. Let me erase this. Number 37. Let's set x squared minus 2x equal to 0. Let's factor. And then we get x equals 0 and 2. Okay. I'll just do it that way for you guys. I'll solve algebraically with you. Let's just confirm that the values we get are the same as the graph. That's fine with me. Finding the zeros, setting this equal to 0, and solving. This factors into x plus 4 times x minus 1. So we get negative 4 and 1. And we can confirm that that's what they have on the graph is negative 4 and 1. That works for me. They say see example 4. Do they factor? Let me go back. No, they just use the graph. I'm going to factor. That was number 38, by the way. All right, number 39. F of x squared plus 2x plus 1. You can see it's crossing at x equals negative 1. Let's see if we can get that same thing out. This is a perfect square trinomial of x plus 1 quantity squared. Therefore, if x plus 1 equals 0, that inside guy, x would equal negative 1. It's the only solution that exists, and that's why there only one solution just hits there only. Number 40. Looks like a similar kind of thing as the previous one. It only hits once. How come? Well, when you factor this, now listen, I'm going to set this thing equal to 0, in which case we're allowed to divide everything by negative 1 or move the other things over. I'm just going to factor the negative out of there and get x squared minus 6x plus 9. So factoring the negative out leads me to x minus 3 quantity squared inside. It's once again a perfect square trinomial. All that matters is if the inside equals 0, what's x? Looks like it is 3. And here they have x equals 3 as your set there. I think they set up to 42, so let's see what happens next. Number 41. We have, oh good, I get to play some factoring of old school variety. F of x equals 2x squared minus x minus 1. Set that equal to 0. And we're going to factor this way. 2x, I could do plus, let's see, minus 1 and plus 1 here. Negative 2 plus 1 is negative 1. So when we solve this, we get x equals negative 1/2 and x equals 1. Positive 1, like that. Now, look at the graph here. Okay, look at this graph. They're scaled every 2 increments is 1. So this is going to be negative 1/2, and that is positive 1. It's not negative 1 and positive 2, right? So look at those scales. That's what we get. Number 42. At this point, I'm just looking at the equations. I'll look at the graph after. F of x equals negative 2x squared plus 3x. There's a greatest common factor of negative x. We set this equal to 0, by the way. Negative 2x squared plus 3x equals 0. Let's factor a negative x out of here, and you're left with 2x minus 3. This is where x equals 0. If 2x minus 3 equals 0, x equals 3 halves. We add 3 and divide by 2. So 0 and 3 halves. 3 halves is also 1.5. So here's where x equals 0. Here's 1/2, 1, 1.5. 3 halves right there. 2 solutions. Sorry, that was 42. Okay, in 43 to 46, approximate the zeros of f to the nearest 10th. Now, I'm just trying to see if, because I could tell you on the graph what the answers are going to be, but because the graphing calculator was the other thing to look at. Oh, they did say to the nearest 10th, not the nearest whole number. So yes, I'm going to use my graphing calculator. If you have one handy, you can take a look at it as well. We do have f of x equals x squared minus 5x plus 3. Now, there are other ways to use this, but the calculator is the ultimate. Here's how we go to the decimal form of it. So I'm going to pop up my calculator here. What I'm going to do is create a y equals equation into this. I'm going to check somewhere between 0 and 1. It's probably going to be around 0.7 or 0.8. And then same thing here, it's somewhere between 4 and 5. We at least know that just based on the curve. That's helpful for us to have. So I'm going to graph y equals x squared minus 5x plus 3. Here's where I can use this calculating feature where I can go by 0.1 and I can look through the table. I'm going to see where this graph goes from positive numbers to negative numbers. And it goes from 0.6 to 0.7. It goes from 0.36 to negative 0.01. So it's closer, because negative 0.01 is closer to 0 than 0.36 is closer to 0, then x equals 0.7 is the best approximation for that. So x is about 0.7 is one of my zeros to this solution set. Now, without using, this is something they said in the lecture portion, and I actually glossed over saying anything about it, but if you knew the vertex, and I know the vertex is at x equals 2.5, if I knew the vertex, this thing is symmetrically going to have another point that's the same distance away. So I already think this number is going to be 4.3 for reasons, because that's 1.8 away from the axis of symmetry, 1.8 away on the other side is 4.3. So that's what I believe this number is supposed to represent, about 4.3. But let's go ahead back to the calculator to figure that out. We could either scroll down until we get there, or I can change my table set here. Oh, I can, I think I can put 4 in, no I can't. So table set, let's start around 4. Let's do the same thing. So you can see at 4.3 it's negative 0.01, and at 4.4 it's 0.36. That's when it goes from negative to positive. Negative 0.01 is closer for the same reason again. So 4.3 is the other approximation. So x is about 4.3, and we get that guy. So those are the two approximations round to the nearest tenth, and we get to do the same thing for the other problems. So number 44. Let's move forward. Let's see the approximations, make our best guess, and go from there. F of x equals x squared plus 3x minus 1. Looks like it's going to be somewhere between negative 3 and negative 4. Negative 3.4, negative 3.3, I don't know. And then maybe around 0.3 or 0.4 here on this other side. So let's go ahead and go back to the calculator. New equation coming up. X squared plus 3x minus 1. Plus 3x minus 1. Okay. Let's start, where was I between? Let's go between negative 4 and negative 3. Negative 4. Let's take a look. So we're going from positive to negative. So same thing as before, the 0.36 and the negative 0.01 kind of show up again. Negative 3.3 is that approximation. So I'm just going to write that. I'll show you that later. So negative 3.3 is the closer one. And then I imagine 0.3 is going to be the other one. So let's start at 0. And we have from negative to positive here, it's closer to 0.3 than it is to 0.4. So 0.3 is going to be the other guy here. Those are my two answers that I get from that guy. Number 45. Y equals, or f of x equals negative x squared plus 2x plus 1. Sorry, wait a second. I guess it's probably around the 0.5 mark on both. It's either 0.4 or 0.5, right? I can't really tell. But somewhere between 0 and negative 1, and somewhere between 2 and 3. So where's my graphing calculator here? Negative x squared plus 2x plus 1. Okay, let's go between 0 and negative 1. By 0.1, so let's see what turns negative to positive. Between negative 0.5 and negative 0.4, it goes from negative 0.25 to positive 0.04. 0.04 is significantly closer than negative 0.25, so negative 0.4 is the better approximation. So x is about negative 0.4. What was the other one between 2 and 3? So probably 2.4 is going to be the other one. Let's plug in 2 and see. So 2.4, yes, is the closer one, then 2.5. So x is also about 2.4. And that's our set right here. And then number 46, kind of sick of the calculator. Negative x squared plus 6x minus 2. F of x equals negative x squared plus 6x minus 2. Negative x squared plus 6x minus 2 minus 2. Okay, so take a look at this. We're going to go... It looks like it's somewhere between 0 and 1 and somewhere between 5 and 6. So let's go between 0 and 1. Probably closer to the 0.3, 0.4 area. Okay, so check out this one. This is negative 0.29 and it goes to 0.24, right? So those are both pretty close to each other. 0.24 is closer than negative 0.29. If I were to get my best guess, I would say it's somewhere around 0.35. But if I'm to round to the nearest tenth, it's closer to 0.4 than it is to 0.3. That's just the math. It's a little closer to 0.4 than it is to 0.3. So x is about 0.4 in that case. And then somewhere between 5 and 6, right? So I'm going to guess 5.6. So let's see. 5.6 is there, and 5.7 is here. And 5.6 is going to be slightly closer to 0.24 than negative 0.29. So 5.6. X is about 5.6. Those are the two answers to that one. There's more than one way to do these kinds of problems here. I could have looked at it on the graph itself, but this is the approximation using the tables. Now we're going to approximate doing this the other way. 47 to 52, approximate the zeros to the nearest tenth if necessary on these guys. So this is where we actually, when they say graph the function, guys, I'm not going to, do they want me to sketch it? Did they do it at the time? Let's see. The graph is shown and approximate. Boy, there was another example somewhere. Oh, here. Sorry. Oh, that was a different question. They said use the graph. All right, I'll sketch the graph. They do say graph, and if their teacher's like, yeah, you have to graph it, we'll go ahead and do that. Because they say if necessary. What if it's not necessary to have to approximate, right? What if it's exact of a value? I want my graph to show that. So f of x equals x squared plus 6x plus 1. So, not factorable. We're going to go out of vertex, excuse me, standard form. The vertex value, x value is negative b over 2a, which is negative 3. The y value is negative 3 squared plus 6 times negative 3 plus 1. That'll be 9 minus 18 is negative 9 plus 1 is negative 8. So the vertex is at negative 3, negative 8. Let's go ahead and plot that guy, or graph that guy. So negative 3, negative 8. It's right there. Regular 1x squared graph. And I did see some different stretch factors, which is nice. That's one of the reasons I do actually want to graph this with you guys and figure what that is out. Over 4 up 16. So right there. That's all I'm going to fit. I can, well, can I fit one more? It's 25 up from negative 8. Yeah, 7. I can't do this. 17? Yeah, it does fit. If I can fit it, I want to. I'm committed. But what are the zeros? They asked to approximate those ones to the nearest tenth. So, this time I'm going to use the other version of what I can do on the calculator here. Instead of looking through the table and seeking it, I'm going to see that, first of all, my graph is correct by looking at where the graph goes. And let's just use the zeros feature on it. So here's what I'm going to do this time. I'm going to graph x squared plus 6x plus 1 on the graphing calculator. So I have x squared plus 6x plus 1. Now, I'm going to sketch this graph here. You can see what it hits like that. Kind of similar to what my graph looks like. My graph looks like this. Right? And then, so it looks like that one, pretty much. But I want to find the zeros. So there's a thing on the calculator where I can find the zeros. I don't know if you can do this. To the left and to the right, it's somewhere between negative 7 and negative 5. I don't know where. The left bound, the right bound, somewhere in between. And it looks like it's here. Negative 5.82. So I'm going to say negative 5.8. And let's find the other one. So sure, to the left of here and to the right of 1, for sure. That's going to be negative 0.17, so around negative 0.2. X is around negative 0.2. So again, you can use the table feature for that. You can follow what I'm doing as well. Either or should work, but that's what we're going to get for those values. And that's what we're getting here. Negative 5.8, negative 0.2. Those look close enough to my graph. All right, number 48. F of x equals x squared minus 3x plus 2. I'll tell you what. I don't have to use the calculator for this one. This is factorable. Now, I'm going to still graph it using my vertex stuff here. So this is going to be, well, they say graph approximately. Yeah, let's see, negative b over 2a. Well, you know what? No, I'm a man. I'm going to go ahead and do this. I'm going to factor this thing. This factors to x minus 2 times x minus 1. I think I'm allowed to do this every so often now. So this gives me x-intercepts of negative 2 and 1. Now those are the answers to them, but they just said graph. So I'm going to get 2 and 1. There's a y-intercept of 0, 2. And there's an axis of symmetry, apparently, now that we're kind of looking at that, right in between 2 and 1 at 1.5, right there. So, another point going across this thing on the graph, the y-intercept is here, 1.5 away, is also this guy. Now, the vertex x value is 1.5. The y value for f of 1.5 is going to be negative 0.5 times positive 0.5, which is negative 0.25. So the vertex is at 1.5 comma negative 0.25 like that. I can do 1, 1, 2, 4, 3, 9, 4, 16, and you can see where we also cross the x-axis by doing it by factoring. I could have used negative b over 2a. I could have, but I wanted to confirm for sure where this hits the x-axis, and it's going to hit at 2 and 1. Nothing approximate about it. These are the x-intercepts, x equals 2 and 1. I already wrote them actually up above, but there they are. Number 49. How long have we gone? An hour 40. F of x equals, this one's not factorable. So, or y equals negative x squared plus 4x minus 2. All right, let's go for the vertex here. This is going to be at negative b over 2a, which is negative 4 over negative 2, which is 2. The y value, let's substitute 2 into here. We'll get negative 4 plus 8 minus 2, which is 2. So 2, 2. Vertex is at 2, 2. This graph goes upside down, so it will hit the x-axis, just not at desirable integer x values. So at 2, 2, we're going to go down 1, or over 1 down 1, over 2 down 4. We hit a y-intercept of negative 2. That was expected. Over 3 down 9. And over 4 down 16. Now, let's approximate the x-intercepts. Let's go ahead and take a look at what this looks like by graphing it on the graphing calculator. I don't know if my curve was the best here, but it looks like it's going to hit somewhere between 0 and 1. Symmetrically, it should hit somewhere between 2 and 3 on the same mark. So my graph isn't perfect. That's exactly why we want to really do this thing on the graphing calculator. So I'm going to go ahead and do that. I'm going to do x squared, or negative x squared, negative x squared plus 4x minus 2. Okay, so it looks like this here. Let's go ahead and sketch its graph, which looks like that. Kind of looks like ours. So just looks a little better. Let's find the zeros. Somewhere between 0 and 1, we're going to have one of them. And that's at 0.585, so 0.6. They say round to the nearest tenth. So x is about 0.6. Now, without using the calculator, I can tell you where the other one is. Let's go back to our graph and talk about it this time. The axis of symmetry is at x equals 2. Okay? X equals 2. 0.6 is right here. How far away is 0.6 from 2? That's 1.4 away. So over on this side should also be 1.4 units away from 2. That's at, so this is 2 minus 1.4. This is 2 plus 1.4. This is going to be x is about 3.4. That's how I was getting the other answers there. The same distance away from the axis of symmetry because they're symmetrical. Don't believe me? Let's go ahead and take a look. If it works out this time, then I think that we can imagine that this should work every time. Somewhere between 3 and 4. So as long as the number's good. So 3.41, right? So about 3.4. That's going to be the answer set there. That's number 49. Okay, number 50. Not factorable again. Y equals negative x squared plus 9x minus 6. Not factorable. Let's go to the vertex set. X is negative b over 2a, which is positive 9 halves, or 4.5. The y value for this, opposite of 4.5 squared. You know what? I'm going to use fractions because I don't know what 4.5 squared is. I should, but I don't. 9 halves squared plus 9 times 9 halves minus 6. That's negative 81 fourths plus 81 halves minus 6, which is positive 81 fourths minus 6, which is 24 fourths, which is, this is faster for me, 57 fourths. 57 fourths is 14.25. So if you want the vertex here, this is going to be 4.5 comma 14.25. That should work out. Yeah, looks good. So we can, I'm trying to think if that'll fit, and I think it does. The only problem is, I don't know if this, I guess it won't hit actual x-intercepts because it wasn't factorable. But 4.5, axis of symmetry there, comma 14.25. It's still going to be very weird numbers when we got to approximate from there. It does go downward, but 14.25, about there. So 1, 1, 2, 4, 3, 9, 4, 16. So let's see. So about right there. And that's kind of all I can really want to fit. So I'm just going to go and do that. Looks like it's going to cross somewhere between 0 and 1. And somewhere between 8 and 9. If I did that right. Somewhere between 0 and 1, somewhere between 8 and 9. So let's go to the graphing calculator. Let's look at what that's going to look like. Graphing calculator. Negative x squared plus 9x minus 6. Oh, you know what? I could have fit still. Hold on. Minus 6 is the y-intercept, right? So, boom. And reflecting across there, we should hit it right there as well. So, okay. I'll fit a little bit more. That's fine. Totally should use that. All right. Look at the graph. Oh, this is going to go too far up that we can see the vertex. That's okay. We can't see the vertex, but you can tell that that's what it's doing. So somewhere between 0 and 1, and then somewhere between 8 and 9, we're going to be hitting these values. Very close to 1 and very close to 8, I believe. So left bound is 0, sure. Right bound is 1, somewhere between 0 and 1. It is 0.725, so about 0.7. So x is about 0.7. Now, 4.5 is how far away from 7? 3.8. So on the other side is 8.3. So I think I'm going to get about 8.3 on the other side. What do I want to do? Calc 0 between 8 and 9. 8.27. So about 8.3. So x is about 8.3 rounded to the nearest tenth. Those are the two answers to that guy. All right, two more of these. Number 51. F of x equals 1/2 x squared plus 2x minus 5. Now, I don't know if this is factorable or not because I don't have this thing in its factored form. I could factor the 1/2 out and see what goes on. I don't think it doesn't sound like it factors to me. But I can still go ahead and try and graph this. So the vertex x value is at negative b over 2a. 2 times 1/2 is 1, so we're just left with negative 2. Let's substitute negative 2 into here to get the y value of this. This will be 1/2 times negative 2 squared plus 2 times negative 2 minus 5. That is a 5. Negative 2 squared is 4. Half of 4 is 2. Minus 4 minus 5, that's negative 7. So we get -2, -7, despite that 1/2 looking a little weird to begin with. That's just more on the stretch factor portion. -2, -7 is where this thing bottoms out. So -2, -7. Now, over 1 up half of 1. Over 2 up half of 4, which is 2. Over 3 up half of 9. Over 4 up half of 16, which is 8. Over 5 up half of 25. 9, 10, 11, 12 and a half. 12 and a half. I'm going to apply as many eggs as I can fit. Over 6 up half of 36, which is 18. What's 18 up from -7's 11. And I think that's probably all I can fit there. We'll just go. We'll just go. We'll just go. Okay. Notice the y-intercept of -5 from the equation. We are hitting that. But notice these x-intercepts are not integers. Sure, it might look like I accidentally plotted. Let's see if I can skinny that up a little bit. There we go. It's not quite at those values that they look like they're kind of at. It's not quite at 2 and quite at -6, but very close to them. Maybe rounded to the nearest tenth, maybe that's what they hit closest to. I don't know. Otherwise, it's probably -5.9 and 1.9 is like one of my guesses here. So let's go to the graphing calculator and see what this one looks like. Or we're going to have 1/2 x squared, 1/2 x squared plus 2x minus 5. I love the graph look. Whee! Like that. It looks very close to that -6 and 2. Now listen, it's not exactly them because it wasn't factorable, but they could round to those. So somewhere between -6 and -5 for the first one. I know that for sure, for sure. Oh, maybe not. Huh. Okay, there's a bounding error. Okay, maybe it's not between negatives. Maybe, let's try that again. Let's say between -7 and -5. Let's be on the for sure for this. Yeah, -5.7. Okay, it wasn't quite -5.9, but I don't know why it didn't. I must have typed something wrong for the bound. So it's around -5.7, which means this is going to be close to probably 1.7 on the other side. So let's see. 0. Maybe I didn't hit 0 first. Between 1 and 2. So 1.7. Okay. All right, that is number 51. And last one from this set, number 52. F of x equals -3x squared plus 4x plus 3. I question whether this might be factorable. Let's see. If I factor out a negative, I get 3x squared minus 4x minus 3. That is not factorable. I'm good. Okay, I won't factor that. Okay, so the vertex, the x value is -b over 2a, which is, well, -4 over -6, which is 2/3. Wow. This is not going to be as fun to graph. So f of 2/3 is -3 times 2/3 squared plus 4 times 2/3 plus 3. So that is -3 times 4/9 plus 8/3 plus 3. -3/9 is -1/3. 1/3. So this is -4/3 plus 8/3. So that's +4/3 plus 3, which is 9/3. That'll give me 13/3. So I have a vertex of 2/3, comma 13/3. And 13/3 is also 4 1/3. And this graph goes downward with a stretch factor of 3. So here's what I do know. Here's what I do know. I do know that this thing has that vertex. So 2/3 over, let's draw that axis of symmetry. This is going to be really hard for me to do some of my points. 2/3 over and 4 1/3 up. So kind of like that. We know we hit a stretch factor of -3, but we also have a y-intercept of 3, which means 2/3 over here, which is 4/3. 2/3 over here, I'm going to have another point. I guess that's not very far away. I wanted to get something pretty ridiculous. But over 1, we get to go down 3. And that looks more like that. What was this? 4 1/3? So, like that? Oh, this is going to be really weird to do. I'm going to do one more set. Over 2, down 4, down 12. So 12 down from 4 is 8, and 1 up from there, 1/3 of the way up from there, kind of looking like that. And then over on the other side is 1, 2 away, and 1, 2 away, so like that. Okay, that's kind of best I want to do. Kind of like that. And kind of like that. Okay. So this is going to hit somewhere between 0 and -1, and somewhere between, well, if I did it a little better looking, probably somewhere between 1 and 2. I'm going to go between 1 and 3 to be sure here. So let's see this one. Let's go to, where's my calculator? Let's go to y equals -3 x squared plus 4x plus 3. All right, let's look at the graph. Yeah, my graph looks the same. Sure. Let's find the 0 between -1 and 0. Looks like my guess there. -1 and 0. And that's going to be -0.5. Now, I'm not daring doing the axis of symmetry thing on this side. It's got to be close to, I think it's still somewhere between 1 and 2, but I can't tell for sure. So let's take a look. Left bound is 1, right bound is 3. Let's find what's in between those. 1.86, around 1.9. Okay, that's where it's crossing on those guys here. So that's your set. Okay. 3 parts. Modeling with mathematics. At a Civil War reenactment, a cannonball is fired into the air with an initial velocity. The function represents the height. Now, I talked about some of this stuff in the lecture regarding how the numbers come in, but you can see 6 feet above the ground's here, 120 feet per second here, and gravity is represented here. Find the height of the cannonball each second after it is fired. You're fired. So, for h equals -16t squared plus 128t plus 6. You know, my calculator, listen, I'm going to use my calculator for a lot of this stuff. Like, I'm going to make a table for each second after it's fired. T and h. Let's make a table. At time 0, I know it's 6 feet in the air. But let's plug in 1 and 2 and 3, etc. until we hit a negative value. Basically, that's what we're going to do. And I'm going to use my calculator to kind of help me on this. So, my calculator only knows y and x instead of h and t, but y is like my h and t is like my x, or whatever, x is like my t. So I'm going to do -16x squared plus 128x plus 6. And I'm going to use that table, but I'm going to just go by ones, and let's write in these values. So at 0, it's 6. At 1, oh, we're going to have a few values. I guess it was launched pretty high. 118, then 198, 246, 262. And you can see that's probably the vertex because you can see the symmetry on the other side. So 246, 198, 118, and 6. 6, 198, 7, 118. So I'm writing these down. 8 is 6, and 9 is -138. 9 is -138. Okay, so here's the table that I wrote. Sorry, the 9 gets cut off just a little bit there at the bottom. But looks like that. Those are the values. Time in seconds and height in feet. That's part A. Part B. Use the results of part A to estimate when the height of the cannonball is 150 feet. Now, there should be more than one answer because it goes up past, from time 1 to time 2, it goes from 118 to 198. Somewhere in between, it's going to hit there. Now, 118 and 198 are both almost the same distance from 150. 118 is 32 feet from 150. 198 is 40, 8 feet from 150. So between 1 and 2, so somewhere between 1 and 2 seconds, closer to 1, and then, and between, now from 198 to 118, 118 is closer to 150, so 7 seconds. Somewhere between 6 and 7 seconds. Closer to 7. Okay. Part C, using a graph, how many seconds is the cannonball 150 feet above the ground? So what we're going to do now is take our equation, negative 16 t squared plus 128t plus 6, set it equal to 150, and we're going to solve. We could use either of those two methods we used in the past. We can either subtract this over, set it equal to 0, and find the x-intercepts, which I plan on doing, or making a y equals this, and find where those two graphs intersect. But I'm going to do the first one. I'm going to subtract 150 over. We'll get minus 144 equals 0 there. Who knows? Maybe that's factorable. I'm not going to bother. So let's go ahead and write that equation out in the calculator. I have the plus 6 already. I'm going to turn it to a minus 144. And now let's find out where these cross the x-axis. It'll be somewhere between 1 and 2, and it'll be somewhere between 6 and 7. So let's go to the graphing calculator, and let's graph that thing. It's going to shoot up high. It's going to come back down fast as well. Somewhere the vertex is way up there, and I can't see it. So between 1 and 2 looks like closer to 1. Between 6 and 7, it's likely closer to 7, because 4 is the vertex. X equals 4 is the x value of the vertex. So between 0 and 2, sure. It is 1.35. So what do they say? Round to the how many seconds? I'm gonna round to the nearest tenth. About 1.4 seconds. And the other one should be then around 6.6 seconds. So between 6 and 7. All right, 6.64, so around 6.6 seconds. 6.6. So when I say closer to 1 and closer to 7, just barely. 1.4, it was really 1.35, but 1.4 is closer to 1 than it is to 2. 6.6 is closer to 7 than it is to 6 on the dot. All right, that's number 53. Number 54, you throw, hey, this is my domain. You throw a softball straight up into the air with an initial velocity. Okay, so it's all the stuff that we did from the last one with a different model. So same kinds of questions. Let's see how we can jump into this one. So h equals negative 16t squared plus 40t plus 5. So same thing as before. Let's make a table for part A. T and h. It should be less values because you can't throw a softball the same way you can shoot a cannon. Of course, it was a Civil War reenactment. Maybe they weren't great. So I'm going to do a calculator thing here. Negative 16x squared plus 40x plus 5. Why don't you take my word for it this time so I can just keep writing on the screen for you. I'm going to start at 0. And obviously that'll be 5 feet, right? You're 5 feet. It says the release point's 5 feet above the ground. And that at times 0 will get 5, which is cool. At 1, I'm getting 29. At 2, I'm getting 21. And at 3, I'm getting negative 19. So it takes less than 3 seconds for the ball to strike the ground. You can imagine that somewhere between 2 and 3, we hit 0, probably really close to 2.5 seconds in. And I don't really see the vertex here because I don't see symmetry. Somewhere between 0 and 1, I think we hit symmetry there. So, or somewhere between 1 and 2 maybe. So, yeah, but those are the values that I'm getting off that when I use it in my calculator. Okay. Part B, they said result when the height is about 15 feet. So for part B, 15 is closer to 5 than it is to 29. So you can imagine it's a little closer to 0 seconds, which is not the way that I want to say it was at 15 feet at launch, because it technically wasn't. So between 0 and 1 second, closer to 0. Closer. And sorry about the handwriting. This is where my handwriting gets a little bad by the end of the day. Between 2 and 3 seconds, right? 2 and 3 seconds. Closer to 2. Now, this is not, the axis of symmetry is not like at 1 or something like that. So this is much closer to 2 than it is to 0. For 0, I'm going to guess it's probably around 0.4 seconds. For 2, I'm going to guess it's really close to 2, like 2.1, 2.2, something like that. So part C, they're going to ask that using graphing calculator. So, or using a graph. I'm not going to graph, but I'm going to use the graphing calculator. We're going to set this equal to 15. Excuse me. We are going to subtract 15 over. So negative 16t squared plus 40t minus 10 equals 0. Let's do that equation. I'll show you that on the graphing calculator in just 1 second. Minus 10. Oh, that's a negative 10. Minus 10. So let's go to this guy. Sketch the graph. It looks like that. I could change the window range and stuff. Let me do that for 1 second. Let's do window. Let's go from -2 to like 5. Let's go from like -5 to like 35. All right, let's look at this graph a little bit better. There we go. Look at that pitch. Okay, so this is 0 and 1 and 2 and 3. So somewhere between 0 and 1, we're going to have a 0 here. This is going to be, I thought the heights got higher than that. Oh, we subtracted 15. I forgot about that. Yeah. Anyway, 0.2817, so around 0.3. And then this is seconds. And then somewhere between 2 and 3. So like I said, it's probably around 2.1 or so. 2 and 3. Remember, this is 15 feet. This is not when it hits the ground. So 2.2. Like that. Okay. Okay, so those are the two ones that we hit there. Those are the better approximations, at least to the nearest 10th. That was part C. Okay, let's go to numbers 55 and 56. Use the given surface area S of the cylinder to find the radius R to the nearest 10th. Are we supposed to know? I know, but are we supposed to know surface area formulas at this point? S equals 225 square feet. I guess you're supposed to know surface areas at this point here. Okay, so surface area of a cylinder. I write SA, not S, but that's okay. Surface area of a cylinder. You got to take the areas of both of your bases, so 2 pi r squareds, plus the circumference of your lateral area here, times the height. To give you that unfolded lateral area. I guess you're supposed to know these at this point? I don't know. Maybe I'm over-embellishing what I'm supposed to do here. So 225 equals 2 pi r squared, r is unknown, plus 2 pi r times unknown height, or 225 equals 2 pi r squared plus 12 pi r. They said do the nearest 10th, so what I'm going to do is subtract 225 over. I'll have 2 pi r squared plus 12 pi r minus 225 equals 0. Listen, r is your variable here, guys. Pi is not a variable, pi is a constant. I was thinking of subtracting, or excuse me, factoring 2 pi out and doing stuff with that, but because 225 can't do that, nah. But I'm going to go and use the graphing calculator on this part. R is going to be like our x. So I'm going to write 2 pi x squared plus 12 pi x minus 225. This one takes a lot of knowledge on this problem. It takes a lot of, you have to know how surface area works, all that kind of stuff. And I don't know when that was specifically instructed on. I don't know if I'm missing something that I should have been stating here. But that's how I would personally go about the problem with all the knowledge I have in my bones. And that's it. So minus 225. Okay, so let's take a look at this in the calculator. Here's what I'm writing out. And I don't know what the answer would be close to. Let's go to our normal standard, if I say that. Okay, so it hit there, and it hits there. All right, this one I don't care about, right? I don't care about negative radii. I care about positive radii. So somewhere between 1, 2, 3. Somewhere between 3 and 4. Let's go ahead and find that one. The 0 between 3 and 4. And that is 3.69. So around 3.7. This radius is around 3.7 feet. 3.7 feet right there. Okay, to the nearest tenth. Okay, number 56. Same stuff. I could probably find some shortcuts as far as how I write what I'd want to write here, but the surface area is 750 square meters. So same thing. This, I don't have to write this part over again, and I can do multiplied by 13 pretty fast. So, okay, yeah, I can probably do this now at this speed. Let's do 2 pi r squared plus, now we're going to do 2 pi r times 13. So 26 pi r, and we subtract the 750 over to set it equal to 0. So yeah, I guess there's just a faster way for me to write that and going straight to the calculator on that as well. So now it's going to be 26 pi times r minus 750. Okay, let's look at the graphing calculator for this guy, and let's go back to the graph appearance. Okay, the negative one must be out of window range. This must be the only one. It's somewhere between 1, 2, 3, 4, 5. I think 6 and 7. 1, 2, 3, 4. Between 6 and 7 somewhere. Let's take a look. The 0 between 6 and 7. 6.21. So around 6.2. R is around 6.2 meters. In this case, they're talking about meters on these guys here. So that should be the answer for that guy there on number 56. Kind of nearly almost done. Number 57, explain how to approximate zeros of a function when the zeros are not integers. So what we've been doing is, when they say approximate, I don't know if they mean with a calculator or not. So without a calculator, we are find the x values between where, let's see, I don't know how to type this in English. Find what two x values show your graph changing sign. So positive to negative, or the other way, or vice versa. Negative to positive. And make your best guess from there. Like, which one's closer? Okay? That's without a calculator. With the calculator, we are going to type our equation, enter input equation into calculator, and repeat above process, but with smaller increments, such as 0.1, 0.01. So I don't know if that makes sense, but we've been looking at a bunch of those. Whichever one's closer to 0, is the better approximation. So it's going to be the same thing there. That works for me. Number 58. Consider the graph shown. How many solutions does the quadratic here have? Explain. And without graphing, describe what you know about the graph of y equals x squared plus 3x minus 4. Okay, so I wish they gave us this question when we were graphing before, because they gave us ones out of window range. Why did they save this for this thing here? So on number 58, part A, notice that this intersects, they intersect together here. I guess they went scaled by 2, but I could have still fit this at -4, 16. The 16 doesn't matter. It's just when I plug in -4 for both, I get 16 for y for both. The question is, what value for x gets you the same y? In this case, -4 is one of them. How many solutions does it have? This is one of them at -4. I think I over-answered part A. And part B, they intersect again at x equals 1. They intersect twice. So they have two solutions. Two solutions Because they intersect twice. Point blank. They intersect in 2 different locations. Part B now asks, without graphing, describe what you know about the graph of y equals x squared, da, da, da. Now, we're not going to do any work on this stuff. What you need to understand, though, is that this is a rewrite of this equation here. This is adding 3x over and subtracting 4 over. So that graph, when you set those on the other side, it's set equal to 0. So how does the graph y equals that work? Where do they cross the x-axis? What are those x-intercepts? Those are where these guys are intersecting together. So y equals x squared plus 3x minus 4 has x-intercepts of -4 and 1. They don't ask me to explain, so I'm not going to type out the explanation, but to explain to you guys once again, what I'm doing is saying wherever these two guys intersected, whatever these x values are the same thing as the x-intercepts you'd get if I set this all equal to 0. They're the same x values. They'll give you different y's, but they're the same x values there, and that's what we're doing. Okay, number 59. Example 3 shows 2 methods for solving a quadratic equation. Which method do you prefer? Explain your reasoning. Well, I guess I prefer the first method here. So, method 1 is where you set it in standard form equal to 0. So, I prefer method 1 because I tend to, because I like graphing out of standard form. I'm not sure. I am comfortable graphing out of standard form, but furthermore, it's because I like finding things in my window range and finding x-intercepts in my window range. Now, method 2 can lead to faster graphing if finding the vertex, if the vertex is really available, if the vertex is readily available. You know, like y equals x squared, it's really easy to graph. But you still have to graph another, still must graph another line. And the points of intersection can be out of the window range. I understand people who might like method 2 more. And I don't mind method 2, it's fine. I think most students wouldn't like method 2 more because a lot of students don't understand it. They don't understand the fact that they're intersect at 2 different spots. Sometimes it's harder to understand the intersection, like the one that just barely crossed and the one that didn't actually hit at all, but it's really hard to tell. And they might not understand what they're doing. And I hope you are over time. After we've done a bunch of these, you understand what's happening for both of them. Number 60, how many different parabolas have -2 and 2 as x-intercepts? Sketch examples of parabolas that have these 2 intercepts. There's an infinite number. So there is an infinite amount. Now I'm going to sketch this to make sure this makes sense here. Okay. So here's -2 and 2. I can have a graph that looks like this. I can have a graph that looks like this. It just goes taller or shorter. I can have a graph that looks like this. I can have a graph that looks like this. Okay. They just kind of wherever. Make it taller, make it shorter, make it whatever. There's an infinite number of them. Basically change the a value, right? This is just some y equals x. Whoops. This is just some y equals a times x plus 2 times x minus 2. Just change a. Change a as long as it's not 0. As long as a is any number that's not 0, then you have an infinite number of quadratic ones that work out there. All right, number 61. Modeling with mathematics. To keep water off a road, the surface of the road is shaped like a parabola. That's true, right? It has some runoff. The cross-section of the road, the surface area is given by this. Yeah, it's going to be a very small stretch. It's not a very curvy road. It's just barely flat, so it can just run off. That's fine. where x and y are measured in feet, find the width of the road to the nearest tenth of a foot. So y equals negative 0.0017x squared plus 0.041x. I'd be hard-pressed to say if there's a common factor or not. I'm just going to go off what they show us here. Looks like the red is representing that cross-section, and clearly x is a common factor, however, which means 0 is one of the answers. I can solve the other one. Watch, I don't need a calculator for this. Let's factor x out. Just don't worry about factoring out numbers. Negative 0.0017x minus 0.041. So either x equals 0 as an x-intercept, of course, or 0.0017x minus 0.041 equals 0. If we add 0.041 to both sides and divide both sides by 0.0017, then x is 0.041 divided by 0.0017. So this is the other answer here. Now, what is that value? Let me calculate that. That part I don't know. But that's what your graphing calculator would do. So 0.041 divided by 0.00. I don't know why I was so excited about that. 0.0017. It's kind of a weird number. Let's go to the nearest tenth, as they said. So it's around 24.1. What is this? Is in feet. So feet and feet. The distance between 0 and 24.1 is 24.1. I also sneeze. Excuse me. And according to this graph, it kind of looks like that's probably where it hits. Around 24.1. So that seems to align with what I did. Didn't really need a calculator except for the very end. So there's that. All right, number 60. Let me pause. I got sniffles. Okay, number 62. A stream of water from a fire hose can be modeled here, where x and y are measured in feet. Negative 0.003x squared. Okay. A firefighter is standing 57 feet from a building. A stream of water from a fire. Firefighter is standing 57 feet from a building and is holding the hose 3 feet above the ground. I assume the 3 has to do with the model. So that 3 is that 3. This 57 is not yet applying. We haven't talked about that. The bottom of a window of the building is 26 feet above the ground. Your friend claims a stream of water will pass through the window. Is your friend correct? Explain. Okay, so here's the layout of like how I imagine this graph thing. This isn't going to be a perfect scaling or anything, but it's like water hose thing. Here's from 3 feet above the ground. Water hose is doing some like that, okay? A firefighter is standing 57 feet from a building. So if the building is right here, this distance here is 57. The question is, when x is 57, are we getting a y value of 26? So 57, 26. About, right? We'll pass through that window. So what does 26 for y equal? Negative 0.003 times 57 squared plus 0.58 times 57 plus 3. Because 57 should be that distance where we get that height for y. So let's check that out and use the calculator. I'm just going to kind of type it out. Negative 0.003 times 57 squared plus 0.58 times 57 plus 3. Okay, I'm getting 26.313. So 26 approximately equals 26.313. That's good enough when they're giving you this model here, yes. As long as it rounds to that nearest whole number, I'm going to be good with that. Explain, I'll show you my drawing. My drawing explains that when x is 57, y is 26. Just about. And listen, the window says 26 feet above the ground. So maybe that's the base of the window, right? Yeah, the bottom of a window. Yes, the bottom of the window is 26 feet above. 0.313 means it's going to go above and go through the window. So above, bottom of window. Totally works out there. So yes. All right, numbers 63 to 65, the last 3 questions. Determine whether the statements always, sometimes, or never true. Justify your answer. Okay, the first one, the graph of y equals ax squared plus c has two x-intercepts when a is negative, always, sometimes, never. This is a sometimes. What they're saying is when you have ax squared plus c, it's just a vertical translation. Excuse me, if a is negative, it's an upside down graph and it's just a vertical translation. But if c is, now they don't say what c is, if c is positive, you're going to have two x-intercepts. If c is greater than 0, 2 x-intercepts, because the graph would have looked like this. If c equals 0, which I imagine they're saying that's not what they're talking about, but that's okay. There's one x-intercept because it would have been on the x-axis right there. And if c is less than 0, there's no x-intercepts. The graph would have shifted down, would have been below, like that. But it's sometimes. Number 64. The graph has no x-intercepts when a and c have the same sign. That would be true. That would be always true. Now, a cannot be 0. So we're not imagining when c is 0. We're saying they're both positive or both negative. So this is one of those things, once again, that like it's either above because a is positive and c is positive, or below when a is negative and c is negative, like that. That's always true. And then 65, last question, the graph of ax squared plus bx plus c has more than 2 x-intercepts when a doesn't equal 0. We're just talking about quadratics in general. Sometimes it's true, sometimes it's not. We've seen a bunch of examples of this. Sometimes C, problem set. We had a bunch. So they're talking about quadratic equations. Oh, more than 2. No, I'm sorry. I thought it just said 2. More than 2. I'm totally sorry. I did not see that. Never. You either have 2, 1, or 0. You can have... So, well, here. You can have 2, 1, or 0. You can technically have an infinite... Well, no, not x-intercept. So you have 2, 1, or 0. This is because a quadratic only passes through something once. Or twice. It can go here, it can bounce back once and do that. It can't do it again. It can't curve back as many times as it wants. It can only bounce back as once. Once at most. Okay, and that'll be it. So I'm glad to have gotten an always, a sometimes, and a never in those ones. I didn't capitalize sometimes, but that's okay. Alright guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I know this video sequence stuff may be going out of order here a little bit right now, and I promise to get other videos up later in the future, but this is section 4.2. Coming up, more solving quadratic equations using other methods besides factoring and graphing. We're going to hear them in the future. So check out the PDF stuff and description stuff down below for any other information that you need, and take care guys. I will see you in the next one.